Okay, today we will consider RC circuit. So this is a simple circuit where we have a capacitor C and then two resistors R1 and R2. Then we have an EMF E, and then we have a switch, and this switch can be positioned in position number 1. If the switch is positioned in position number 1, then the capacitor will be charged. If the switch is positioned in position number 2, then the capacitor will be discharged across resistor R2. So the first question that we want to solve here is the capacitor is not charged at the beginning, so there is no charge at the beginning on the capacitor, and the switch is in position 1. So the capacitor is being charged. What is the charge on the capacitor after a very long time? After a very long time, what is the charge in the capacitor? The maximum charge, I would say. So this is what we are gonna solve today. So let's put the capacitor or the switch here. Then, so what do we have? We have a circuit that is where the capacitor is being charged. So there are two methods that we can do. A qualitative method, how to solve this problem. I will start by a qualitative method. Qualitative, I will call it qualitative. This qualitative method is to look at the fact that the circuit becomes very simple. It becomes R1 and then R2, okay? And then the potential difference across the capacitor is also equal to the potential difference across the resistor, okay? A resistor number 2. So VC is equal to VR2, and then we can use the voltage divider rule that gives us VR2, which is also equal to VC. It's equal to R2, R1 plus R2, and times the EMF, E. And since the capacitor, the potential difference across the capacitor is equal to VR2, this means that it's also equal to R1 plus R2, and charge after a long time stored into the capacitor will be equal to, of course, VC times the capacitance, and this will give me the charge is equal to R2C over R1 plus R2 epsilon or EMF. This is the qualitative method. Now we can go and do the quantitative method, which means an analytical method using the Kirchhoff's law. Here I will start a new page to explain this. So here I will use the quantitative method or analytical, I will call it analytical method, where I will use the Kirchhoff's law. So my circuit will become the following. This is the EMF, okay, and this is a resistor R1, and this is capacitor C. This is resistors R2, sorry, and then the circuit is closed. Then I will use the current. This is I, and this is I2, and this one I will call it IC. Okay, then I start looking at the Kirchhoff's law rules. So let's say I can start from the first loop number 1, and this loop number 1 will give me the EMF minus R1I minus VC is equal to 0. This I will call it rule number 1. Then I will go to the second loop, this one, which is very simple. So this one will give me the potential difference across the capacitor is equal, which is this one, this is the VC, is equal to the potential difference across resistor number 2, which will give me equation number 2. In addition to that, I know that the current is equal to IC plus I2. So I have three rules here, three rules. This is 3. So I can do 3 in 1, which will give me directly epsilon minus R1 IC minus R1 I2 minus VC is equal to 0, which I can simplify or group into E minus R1 IC, okay, minus R1 over R2 plus 1 VC is equal to 0. In fact, what I did here is I used equation 2 here. I used equation 2 in this one. In this equation 4, I will call it 4. Okay. So what I did is I replaced I2 by its value. So this will give me E minus R1 IC, and I know that I2 is equal to VC divided by R2, and then I group this both of them. Okay. So this I will call it equation 5. In addition to that, I know that VC is equal to QC. This is the charge stored in the capacitor at time t. Okay, so again, I can replace, and also I know that IC is equal to dq over dt. This is the current inside the capacitor, or a current that is flowing across the capacitor. So then I place here R1 IC is dq over dt minus R1 plus, so this is R2, R1 plus R2, okay, over R2 VC. I can replace VC by its value, Q over C, which will give me 0. I will put alpha, just for simplification, I will put alpha is equal to R1 plus R2 over R2 C. So this will become alpha. Okay, just for simplicity. So then I have the EMF minus R1 dq over dt minus alpha q is equal to 0. So the idea, this is a differential equation in Q. It's a differential equations. Differential equations. It's a differential equation. Equation on Q, which I can easily put as dq over dt is equal to E over R1, just rearranging the formula, minus alpha over R1Q. And then it gives me which dq over dt is equal to alpha over R1, then E over alpha minus Q. Okay, this is the equation that I want to solve. So what I can do here is I can put dq over E over alpha minus Q is equal to alpha R1, which I can also put as dq over Q minus E over alpha is equal minus alpha over R1. I can integrate this between 0 and the charge at any time t. Okay, so the integral of this will give me ln of q minus epsilon alpha minus ln of minus e over alpha is equal minus alpha over r t. So the integral of this part gives me ln, and the integral of this part gives me at the time t, because it's a constant. Well, I can also do q minus e over alpha over minus e over alpha is equal to minus alpha over r1 t. Okay, then I can get rid of the ln by going to the exponential. So q minus e over alpha over minus e over alpha is equal to exponential of minus r1 times t. And this gives me easily, we can easily see that the charge will be equal to e over alpha 1 minus exponential minus alpha over r1 t. Okay, this is okay. And what is we know that alpha is equal to r1 plus r2 over r2c. So qt, final qt, will be r2c over r1 plus r2 e 1 minus exponential minus alpha r1 t. And you can easily see that at t, when t goes to very large values, which means the capacitor is completely charged, then the exponent goes to 0 and q becomes q max. And you can see it is equal to r2c over r1 plus r2e, which is what we observed or what we obtained qualitatively. So r2c over r1 plus r2 epsilon. Now, the good thing here is that with this equation, now we have an equation that gives us the charge at any moment and also the current at any moment, because we can do IC, it's just the derivative of the charge. Okay, so this is what we have. Then we can also ask another question. Now, if we move the switch to position 2, now we know that the capacitor is charged and the switch is moved to position 2, which means the circuit becomes this C R1 R2. So the capacitor will be discharged across an equivalent resistor that is this one. So the equivalent resistance will be equal to R1 R2 over R1 plus R2, and we can easily see that the charge during this discharge, so the capacitor is discharging, so the capacitor is discharging. This means that it's equal to Q max, the equation of discharge, which can be easily solved here using the Kirchhoff's law also, exponential minus T over the equivalent times the capacitance of the circuit. So this is, and again, we can also calculate the current during the discharge, which is also the derivative of the rate of change of the charge. So that's just to give you that usually when you have this kind of a RC circuit, you can use the qualitative method to estimate the charge at t equals 0 or at a very large time. But you can also use the Kirchhoff's law to calculate the instantaneous charge and the instantaneous current at the capacitor during charge and during discharge.